Where there's motion, there's energy. And so it doesn't surprise that a vibrating string carries energy. Well, anything that moves, vibrates, has energy. And in fact, the vibrating string is a bunch of harmonic oscillators. Now, you can have waves, traveling waves along a string, and these will be transverse oscillations that carry energy. So we'll calculate that in this lecture. But then I want to tell you about something that's more interesting and more surprising, and that is the difference between phase and group velocities. Now, in the newspapers or elsewhere, you might have heard that scientists have used Bose-Einstein condensation to slow down light to just such speeds that you can almost walk along with it. And this seems to violate the theory of relativity. And people ask, but how can you have light slowed down? Doesn't that contradict Einstein's basic assumptions? And the answer is no. The difference, we shall see, lies in the difference between phase and group velocity, and we'll explore that. And finally, we'll look at how frequencies can shift depending on whether you approach a source or run away from it, and that will be the Doppler effect. Let's first discuss energy flow down a string. So, what we're going to consider is a string. Let's shake it at this end, and there's a wave like this that propagates in this direction. Now, take a small portion of this string here. So let's look at this much. And so this much is the distance dx. So this much here is dx. It is at a height, let's call that y. So this much here is y. And of course, this is the y-axis here, this is the x-axis here. So the kinetic energy of this little piece that I've drawn over here will be half the mass of that little piece, let's call that delta m, times the speed squared of this little mass. So that is dy by dt squared. Why have I written partial y by partial t instead of dy by dt? Well, that's because I'm doing this at fixed x. Now, we're dealing with a uniform string or rope or whatever, and so rho is what we call the mass per unit length earlier on. That means that delta m over here is going to be equal to rho dx. So in other words, this the bigger this little piece over here dx, the more the mass. Okay? So then if I want to get the total kinetic energy of all the little pieces of string, then I must add them. And so the kinetic energy will be simply the half rho factor over here into the velocity squared. So dy by dt squared. Now, where should I integrate from? Well, it depends how much of the string I'm considering. So if I'm considering, let's say, the portion from here up till here, then I will integrate from 0 to lambda, lambda being the wavelength over here. And of course, this doesn't have to be periodic, but if we can take it as periodic. If it's non-periodic, then we can open it up in a Fourier series. So now, let's consider a periodic wave. And as I said, a non-periodic wave can always be decomposed into periodic waves. So let's begin with this. And we'll take this y of xt to be of the usual form. So let's take it to be the amplitude A sine of kx minus omega t. The bigger the value of A, the more the displacement y. And of course, omega is the frequency and k is the wave number, which is essentially 1 over the wavelength. Okay, so now we can calculate y dot. Y dot is another word for dy by dt. It's sometimes more convenient to use this. So what's y dot? Well, if I take the derivative of this, of sine of kx minus omega t, then I get minus omega a cosine of kx minus omega t. And so therefore, I have dy by dt squared as being omega squared a squared cosine squared kx minus omega t. Which means that the total kinetic energy will be just this half rho omega squared a squared and then the integral of cosine squared kx minus omega t. At this point, I remind you of a useful identity. And this is one that you really do need to remember. And that is that that cosine of 2 theta is equal to 1 minus 2 cosine squared theta. So this is 2 times the angle here. And this says that this cosine squared is half of 1 minus cosine of 2kx minus 2 omega t. So now I have a formula for the kinetic energy of the string, and now let's decide upon where to put the integration limits. Now suppose I decide that let's take the distance from here to here. In other words, the wavelength 0 to. So I'm integrating from here to here. Now, cosine of 2, this cosine over here is a function that goes down and then up and then down and up. And if I integrate over a complete wavelength, I will get 0 because the area over here plus the area over here will cancel the area over here. So therefore, integrated over one wavelength, this will give 0. And so therefore, the kinetic energy will be 1/4 rho omega squared a squared times, well, lambda, because integral dx from 0 to lambda is just equal to lambda. Now recall that for a simple harmonic oscillator, the kinetic energy and the average potential energy are equal. So if you have that usual kind of harmonic oscillator, so let's say that there is this over here, sometimes the energy is purely potential, sometimes it's purely kinetic, and as it bounces up and down, on the average, this and this are equal. So therefore, the total energy is double this. So it's half rho omega squared a squared lambda. Now, that's the energy in one wavelength here. This, the wave is moving with speed v. And you remember that omega is equal to vk. Now, this means that in 1 second, in unit time, 1 second or unit time, the amount of energy carried is rho omega squared a squared lambda over t. That's because in time t, the time period, this point will have moved here. And so, let's recall that this lambda is 2 pi over k, and t is 2 pi over omega. So this is half rho omega squared a squared omega over k, but omega over k is v. And so therefore we've reached our final result that the rate of transport of energy is half rho omega squared a squared v. Now, let's reflect upon this formula a little bit. First of all, the most important thing is that the amount of energy flowing down is proportional to the square of the amplitude. Not to the amplitude, but to the square. Secondly, this is pretty obvious, the faster the wave moves, in other words, the bigger v is, the more energy will flow. Next, that there's omega squared over here. In other words, if the frequency is greater, then the energy that flows is also greater and again goes as the square. And finally, you have rho over here. Why do you have rho? Well, that's pretty clear from the derivation here, because the kinetic energy is half mv squared, and the potential energy and the kinetic energy are basically equal for a harmonic oscillator. I want you to look at this animation which you've seen many times before. Now, look at it in two ways. Focus first your attention upon any one of the particles, so you'll see them going up and down. Now you can see it clearly. All right. Now let your eye follow the wave down to the right. So you see something that is moving down, and that thing is really the energy that's being carried by the wave. We will now learn how to add two sine waves to each other. Okay, now let me take one sine wave, and this will be a traveling wave, to be the amplitude times either cosine or sine. Now let me take this. So k1x minus omega 1t. And let me take the other wave to be also a function of x and t. And I could take a different amplitude, but it's a little easier if I take the same amplitude. We learn how to deal with separate amplitudes if there was a here, b here later. And what I'm going to do is now take a different wave number k and a different frequency k, omega here. Now, both of these will be traveling with the same velocity v. The speed v is the same for both. So omega 1 is v k1 and omega 2 is v k2. Let's take the sum of the two. So if I take y1 of xt plus y2 of xt, well, that's pretty, I just have to add this to this. And I need to know what this is. So for this, I will ask you to recall. You probably saw this in school, but let's repeat it here. That if you take the cos of A and you add it to the cos of B, then this is 2 times the cosine of the sum of the two, A and B, times the cosine of the difference, A minus B over 2. And now let's apply this to this plus this to calculate that. Okay, so y1 of xt plus y2 of xt, that's just going to equal to 2 cosine. And now here it will be k1 plus k2 over 2x minus omega 1 plus omega 2 times t, and cosine of the difference now. So it will be k1 minus k2 over 2x minus omega 1 minus omega 2 t. Now, as it is, we're not learning too much from this, but let's take a particular case. So, take a particular case where the two are quite close to each other. So, omega 1 and omega 2 will differ by only a small amount, and consequently k1 and k2 will differ by a small amount also. Okay, let's take, I'm just going to manufacture an example. I'll take omega 1 to be 102, omega 2 to be 100, and let's take v equal to 5. Well, in that case, half of omega 1 plus omega 2, so that's what I need for here, that will be equal to 101. If I take the difference and divide by 2, well, that's just equal to 1. If I now calculate k1, well, k1 is 102 divided by v, and so v here is 5, and so this is 20.4. k2 will be just 20, and so half of k1 plus k2 will be 20.2, and half of k1 minus k2 will be 20. Okay, so what I have now is that the sum of the two is 2a cosine of 20.2x minus 101 t cosine of 0.2x minus t. Now you see, what we have before us is the following. So this here, this cosine is very rapidly oscillating. It's oscillating both because of time and because of space. So what we have here is fast oscillation and a short wavelength, of course. Short wavelength because this k here is large and lambda is 1 over k essentially. And this over here is the opposite. This is slow oscillation in time, and this has got a long wavelength. So there's something very fast being multiplied by something. So this thing over here is changing very fast with time. And this is just changing the amplitude of that oscillation. And so what we expect is the following, that there's something very fast, up and down and up and down and up and down like this, and then it's modulated. That is to say, so there is going to be an envelope over here, this, which is going to have an amplitude. That amplitude will be this. Let's now look at this in an animation, because I can't draw cosine of this frequency very well on this paper here. So let's have a look at something that will allow us to understand why there's fast oscillation and there's slow oscillation. Okay, so here's the animation. Here is Y1 and here is Y2. The two frequencies can be made close to each other or made very different from each other. But now look below here. So I'm just going to stop this for a while so that you can see more clearly. This is Y1, this is Y2. When we add them together, there is this fast oscillation. So the fast oscillation has got frequency omega 1 plus omega 2 over 2. But then there is also a modulation. That is to say, the amplitude of this fast oscillation changes according to what you saw. It is omega 1 minus omega 2 over 2. And so what we are seeing now is that the addition of two sine waves to each other is giving us what is called a beat pattern. So if you beat one wave against another wave, what you get is a sum that reflects both the fast oscillation, which comes from the sum of the two, and the difference, the slow oscillation, which comes from the difference of the two. Let's play around a little bit with this. So now what I'm going to do is change the frequency of, let's say, one of these and make the difference greater. Now, if I make the difference greater, you can see that the modulated pattern becomes this. If I make it lesser, then it becomes this. You can play with this animation. The URL is given on the screen. Now you see this beat pattern over here is actually carrying information. This, a plain sine wave or cosine wave, carries no information. All you know is whether it's there or not. But when it is beating against this, then something is changing. Something is going up and down. And these are called wave packets. We have made a packet of waves starting by the addition of two waves to each other. I am now going to discuss phase velocity and group velocity. I've already discussed phase velocity, but we shall quickly recap that. So when I have a plane wave, when I have a wave, the ratio of omega to k is what we call V, and that is the phase velocity. You saw that for a string, this v is square root of t over rho. For an electromagnetic wave, this phase velocity would be the speed of light, etc. Now, just in the previous slide, you saw that we took the sum of v1 of y1 and y2, and we saw that one of these was a cosine of k1x minus omega 1t, and the other one was cosine of k2x minus omega 2t, and we added them together and we got 2 cosine of the sum. So k1 plus k2 over 2x minus omega 1 plus omega 2 over 2t cosine of the differences now k1 minus k2, and the differences of the frequencies as well. Okay, so this was the wave packet that was traveling, and now I'm going to define the group velocity. So let's call that Vg. Vg, group velocity, as the following. It is equal to not omega over k, but the difference of the omegas divided by the difference of the k's. So I'm going to define this. These three equivalents over here means this is a definition. So this is omega 1 minus omega 2 divided by k1 minus k2. So I'm looking at this as a wave packet. And this thing is traveling along. How fast is it traveling? Well, that means if you want to keep the phase of this thing here constant, then this must be equal to that, or it could be this equals that plus a constant. So this is, now let's see if both of omega 1 and omega 2 are equal to v, then this omega 1 is v times k1 minus, and omega 2 is v times k2, and we divided by k1 and k1 minus k2, and this is equal to v. So when the frequency and wavelength or wave number have a constant ratio, then there's no difference. Vg will be equal to the phase velocity, v. And I could call this Vp for phase velocity. Let's do this. Let's call this the phase velocity. And so that happens if omega is equal to Vk, independent of k. Now, that's what is called the situation of no dispersion. No dispersion means that the frequency divided by k is independent of k. So that was the no dispersion case. But now, imagine two slightly different frequencies added together. What that means is that suppose that K1 and K2 are very close to each other. Omega 1 and omega 2 are very close to each other. So Vg then is, well, if omega 1 and omega 2 are close and K1 and K2 are very close, then this is exactly what you call a derivative. So then Vg becomes d omega by dk. Now, if we write it this way, as d by dk of omega equal to v, which now depends on k times k, then this has two parts to it. So this is dv by dk into k plus v of k, v of k into 1. So you can see that if v is independent of k, that is to say in the no dispersion case, the group velocity and the phase velocity will be equal to each other. But in general, d omega by dk is not going to be equal to a constant v. So if different frequencies travel at different speeds, then the group velocity and the phase velocity will not be equal to each other. Let's take an example. So, for light, the group velocity and the phase velocity are always equal. That's because omega is equal to ck. So, V is the same as V phase in vacuum. So when light travels through a vacuum, all the different frequencies travel at the same speed. But if they go through a medium, then Vg that's not equal to the phase velocity in a medium. In fact, the group velocity can be very small. That's because you could have dv by dk over here being negative. So essentially, the question is, what is omega as a function of k? Now, this is what is called a dispersion relation. And many possibilities exist for different physical systems. So if you have light, well, omega equals ck, and that's light in a medium. Without, that's light traveling in vacuum. So omega will be equal to c times k, where c is the speed of light. But it could be different for, let's say, a wave of electrons. Now, if I have electrons, then I can, you know that electrons are waves, and when you learn a little bit of quantum mechanics, you'll see that omega is actually Planck's constant h bar k squared over 2m. And that means that this omega is growing with k not linearly over here, but it's growing quadratically. And so the quadratic grows like this. They both start from 0, but the square, the quadratic, grows much more rapidly. In this case, the phase velocity, well, let's calculate the group velocity here. So Vg, this is equal to d omega by dk. And now d omega by dk is h bar k over m. And that's just the momentum h bar k divided by the mass. That's what you expect for a particle anyway. But If I look at the phase velocity, well, the phase velocity is omega by k. And if I take omega as h bar k squared over 2m, well, that's equal to h bar k over 2m. But this is half the group velocity. So for light, or you could say photons, the group velocity and the phase velocity are exactly the same in vacuum, although not in a medium. But for electrons, the group velocity and the phase velocity are not equal. The group velocity is twice the phase velocity. I'm now going to take a different topic, harmonic generation. And this is something of great practical importance, especially in electronics. Normally, a wave has frequency omega, and this omega remains constant. So a wave, if it begins with frequency omega, remains having frequency omega, except that if you have what is called a nonlinear medium, then this omega can become double of what it was, maybe 3 times what it was, or any number of times what it was earlier. This only happens in nonlinear systems. So this might sound difficult, but it's not. Let me explain this. So suppose you have an amplifier. What does an amplifier do? It takes in a signal. Let's say that signal is F, and it simply multiplies that by some constant. So if it's an amplifier that has gain 10, that means that whatever you put in is multiplied by 10. So the input and the output are completely related to each other by this number A, called the gain. So this, we could call this an amplifier here, just to be sure. That's a linear amplifier. So F remains F. It's simply multiplied by a number. But then some amplifiers are not perfect. And you could have distortion in an amplifier. So a nonlinear amplifier could, for example, take an input F, and out would come not just AF, but a little bit of F squared, maybe a little bit of F cubed, and so forth. A designer of electronics would want to have epsilon equal to 0 if he wants the amplifier to be an amplifier of music. In that case, the best amplifiers have got epsilon less than 1 part in a million. But in old times, this epsilon could not be made very small. So let's see how this nonlinear amplifier acts as a means of changing the frequency. So let's put in as input f of t as a cosine of omega t. So if this is a sound amplifier, then this omega will be in the range of sound frequencies, which means from somewhere between 20 hertz to 20,000 hertz. Well, then what comes out will be, so this is the input. The output will be A times whatever there is, whatever you put in, and then some little bit of epsilon. This epsilon could be quite small, maybe it's a tenth, maybe it's a hundredth, whatever, times f squared, cosine squared of omega t. Now you see that this, now you remember that cosine of 2 omega t is equal to 1 minus 2 cosine squared of omega t. And so this is actually equal to a cosine omega t plus epsilon into half 1 minus cosine 2 omega t. And if you just rewrite this a little bit, this is half epsilon plus a cosine omega t minus half epsilon cosine 2 omega t. So we have the original signal multiplied by the gain a. That's a good thing to have for sound, for example. But now there's a DC, we'll call this a DC component. This is the original frequency. But now notice over here that the frequency has doubled. And so if you were to listen to something that has got a lot of, that in which epsilon is not small, you would notice a frequency which is twice the frequency of what is originally there. And this would give you an unpleasant sound to hear. What about a different kind of nonlinear amplifier? Well, you could have a term over here of epsilon times f cubed, in which case you would get over here either sine or cosine of 3 omega t. So then there would be frequency tripling. So you can have, in a nonlinear system, the frequency becoming double, triple, 4 times, and so forth. Now this is something that is also very common in lasers. Waves are there in every physical system, and this is an important thing, that harmonic generation takes place when you have nonlinearities. There's another way in which the received frequency is different from the emitted frequency. And so we're going to talk about now the Doppler shift. Now this is something that is very commonly observed. You can hear a car approaching and its frequency is different when it's coming towards you and when it's going away from you. Well, here I'm going to take the first case in which the source of waves is fixed and the observer is moving. Well, let's see exactly what's involved. So we'll take a source over here, call it S. S puts out pulses after every t seconds. So after time t. In other words, the frequency of this source, so it's emitting waves all the time with frequency nu equal to 1 over t. There's an observer over here, and let's say that when this started emitting waves, that distance was L. But this is now moving towards the right, and let's call the speed of that movement v. Then any wave that is emitted from here has to then catch up with this. So let's now take the following situation. There's a pulse emitted at time t equal to 0. It's received at time t1. Okay, so the pulse leaves here at time t equal to 0. It's traveling with speed. So speed of waves, we'll call that c. The reason I'm calling it c is because I've already used v over here. Okay, so that pulse is emitted at time t equal to 0, received at time t1, and so obviously the time then has to be the following. It has to be the total distance that the pulse has to travel from here to here, which is the initial distance plus how much distance was traveled in time t1. So it's L plus Vt1 divided by c, which means that from here you can see that t1 is equal to L over c minus v. So just take this on this side, ct1 is equal to this, L plus Vt1, and so t1 is this. Now let's take a second pulse. That's emitted after time t. And this time t is the time period. So this goes blip and then blip again after time t. Let's say that it's received at time t2 by the observer, by O. Okay, in this case, the time t2 will be, of course, t plus the distance plus the time taken for the pulse to travel all this distance in time t2. So we'll have L plus Vt2 divided by c. Now again, I can take t2 on that side, and I get from here that t2 is equal to, so I take this over here, and so I get t2 is equal to c into 1 minus v over c plus t over 1 minus v over c. But you see this over here, if I just work this out, this is L into c minus v. That's exactly what we have over here. And so this is t1 plus t over 1 minus v over c. That means that the difference in times t2 minus t1, let's call that delta t. So the first pulse is received at t1, the second pulse is received at t2, the difference in the times is delta t, and that's equal to t over 1 minus v over c. Now notice that if v had been 0, then of course delta t would have been equal to the time period t itself. But now it's going to be greater if v is positive. So therefore, the frequency, received frequency, I'm going to call it nu prime, is now 1 over the difference in the times of reception of the two pulses, and this is now 1 over t into 1 minus v over c. But this 1 over t is exactly this thing, nu over here. And so what we've achieved is the Doppler shift formula, where the observer is running away from the source. And so you see that so this is the received frequency, and this here is the emitted frequency, that they are not the same. that in fact the received frequency is less than the emitted frequency if V is positive. Now, on the other hand, if V was in this direction, so as you run towards the source, then the frequency increases. And that's a very important result. Now, here, remember the assumption was that these waves are traveling at constant speed with respect to whatever medium there is, with speed of the waves being c. Okay, so that's a very important formula for the Doppler shift, and it'll come in handy in many places. Well, now let's take the second case of the Doppler shift again. And in this situation, what I will do is take the observer to be fixed and the source to move. Now, this is going to be a little different. So, again, we have a source, S, and here is the observer. And this is emitting waves separated in time by t. So the first pulse emitted by S is received after time L over C. So initially the distance between here and here, that's the observer here, was L. And so the time between the emission of this pulse and the reception of this pulse was L over C. And that's what we'll call T1. Now the second emitted pulse by S is received after less time, because you see, this has now traveled a distance which is, so in the time t, this has traveled a distance vt. And so the time now at which it is received is going to be L minus Vt divided by C. And that's T2. And of course, that's T plus that, because it was emitted at time T. And so now T2 minus T1 is what's important. And so delta T, which is the separation in the times between when the second pulse was received and when the first pulse was received, that is equal to T plus L minus Vt over C minus L over C. And now this is equal to 1 minus V over C times T. So therefore, the received frequency, nu prime, which is 1 over delta T, is just this, 1 over T into 1 minus V over C. And this is equal to nu over 1 minus nu over C. And so this finally is our result. That as the source runs towards the observer, the observer sees that the frequency has gone up. So this V over here is positive, and so therefore this 1 minus V over C is smaller than 1. And I need to correct over here as well. Okay, so we have two formulas now. You saw that this is for the fixed observer, and the other one that you just saw was different. That was nu prime is equal to nu into 1 minus V over C. That was so, of course, these V's mean different things here. So, of course, these V's mean different things here. In the case that we derived, this V was the speed at which this source was running towards the observer, and so the frequency goes up. In this case, V was the speed at which the observer was running away from the source, and so the frequency goes down.